now a couple of minutes. So, since we are in the field, we usually wait at least a couple of minutes after the regular time to start to let everybody come in the same time, which is not necessarily on that perfectly on time.
Привет, Миш. Yes. So why are you laughing? Did I make a misspell?
CH, you should read X.
Huh?
We try to understand what SUSTech. Why not CH? We just to answer this.
Good question. It is LaTeX, there is tech, there is SUSTech.
Perhaps we should start. So I just want to say it's a pleasure to receive here at the Colóquio from IME Professor Efim Zelmanov, who is from. Oh, so I have to speak louder for the people here, and everyone here and there, please don't mind if I'm shouting to you. So it's a pleasure to receive Professor Efim Zelmanov, which is the scientific director of the International Center of Mathematics from. I'm too shy to do that. Okay. It's a pleasure to receive Professor Efim Zelmanov, which is the scientific director from the Institute for the International Center of Mathematics from SUSTech. Professor Zelmanov has received the Fields Medal in 1904 and is a member of several different Academy of Sciences, which including the American Academy of Science, the Chinese Academy of Science, and the Brazilian Academy of Science. And Professor Zelmanov is going to speak about the growth of algebras. It's really a pleasure for us to receive you here. Thank you.
Thank you. Should I also use it?
You don't need it.
Oh, yes. Well, it's by far not my first talk at this university, and it's always a great pleasure. This time I lost my voice. I have cold, so we'll broadcast my coughing. Well, I will talk about all things, groups, algebras, monoids, even languages that are infinite and finitely generated. They were not born infinite. They grew to become infinite. And we will discuss that process. So let us start with groups. Let G be a finitely generated group, which means that an arbitrary element can be represented as a product of generators and their inverses. If we bound the length of this product, say by n, then this set is finite. If we consider the Kelly graph of this group, vertices of Kelly graph are elements of the group, and two vertices are connected. If one element is multiplied, if one element is obtained from another element by multiplication by a generator or its inverse. So then this is just a ball of radius n with the center at the identity element. These balls grow, their union is the whole group, and this is a growth function of the group, relative to this set of generators. Unfortunately, this growth function depends on the choice of generating system. Therefore, we will need to introduce some equivalence relation. Given two increasing functions on natural argument, say two real numbers that are greater or equal than 1, we say that one function is asymptotically less or equal than another function if there exists a constant such that we always have this inequality. If f is asymptotically less or equal to g, and g is asymptotically less or equal to f, then we say that f and g are asymptotically equivalent. This is a very rough equivalence. Two polynomials are equivalent if and only if they are of the same degree. All exponentials are equivalent. If a group G, if you have two finite generating subsets, then their growth functions are of course different, but they are asymptotically equivalent. So the growth of a group is not a function, it's a class of equivalence of a function. This concept originated in late 50s and 60s in geometry. It was first studied by Schwarz, Eufremovich, Milner. If you have a Riemannian manifold and fix a point, then the growth of volumes of balls at that point is asymptotically equivalent to this growth in the fundamental group. And the first is a geometric characteristic of the manifold, the second is topological characteristic. And another reason to be interested in growths is just a question of comparison of two groups. If you have two finite groups, you may discuss which of them has bigger order. But if you have two countable groups, what can you do? You may discuss which group grows faster. Now, if we have monoids, monoids are just semigroups with identity, so all the same, but without inversion. And in absolutely the same way, we consider all products of lengths up to n, growth function, asymptotic equivalence, and so on. And we will consider even hereditary languages. Suppose this is a subject that is much discussed outside of mathematics. Let us suppose that we have a finite alphabet and a list of bad, prohibited words. Now the language consists of all words that do not contain bad words as subwords. We also add 0, so it is a monoid with 0. And it's a monoid presented by generators and relations. The letters are generators and bad words are relations. Stepin and Grigorchuk found some explicit functions for growth of these languages. Now let's talk about algebras. Let F be a field. We consider a finitely generated algebra, so this algebra is generated by a finite dimensional vector space V. Then Vn is the span of all products of lengths up to n. In any case, this is a finite dimensional space. And these finite dimensional spaces grow, the union is the whole algebra, and again, the growth function is the dimension of Vn. This growth of algebras was first studied by Gelfand and Kirillov in '65. They needed to prove that two countable dimensional algebras are not isomorphic. So they introduced this invariant. If this growth function is polynomially bounded, so it is less or equal than some polynomial, and by the way, this property is asymptotically invariant. then the the infimum of degrees of these polynomials that bound the growth function is Gelfand-Kirillov dimension of the algebra A. So they needed to show that two algebras are not isomorphic. They just computed their Gelfand-Kirillov dimensions, and that was it. In '68, John Milner published a very influential survey in Mathematics Monthly. I don't know if you know, Mathematics Monthly is not a research journal. It's a journal for undergraduate students. Well, in that survey on growth, he formulated two problems. The first problem: is it true that a group has polynomially bounded growth if and only if it has an nilpotent subgroup of finite index? At that time, it was known that finitely generated nilpotent groups have polynomial growth, and growth was known too. So the question was, are there different situations when a group has polynomially bounded growth? And in the same survey, he asked, do there exist groups with intermediate growth? That is, growth that grows faster than any polynomial and slower than any exponential. Both problems were solved in early 80s. In 1980, Misha Gromov proved that the answer to the first question is yes. Groups with polynomially bounded growth are virtually nilpotent. And in 1983, Rostislav Grigorchuk constructed examples of finitely generated infinite groups with intermediate growth function. And I should say, that's only my personal opinion, that in both cases, proofs were more important than results. It's results of huge importance that groups of polynomial growth are virtually nilpotent. But the proof was the beginning of geometric theory as we know, geometric group theory, as we know it now. The concept of Gromov-Hausdorff limit, asymptotic cone, and it all appeared in that paper. Later, there were other proofs that kind of circumvent this. Proof due to Kleiner. It would be a tragedy if that proof appeared before Gromov's proof. And the examples of Grigorchuk were also independently important because these groups are more than just counterexamples. They appear in dynamical system, ergodic theory, number theory, in many, many contexts. You know, there are counterexamples that are only counterexamples, and there are counterexamples that are important by themselves. Okay, now, since I'm talking about recent progress, so what is the growth of the Grigorchuk group? Let's consider this cubic equation. This cubic equation has a root which is approximately equal to this. And the logarithm of 2 with the basis of this root is approximately equal to this. Now, Bartholdi, Erschler, and Zhang proved that the growth of the Grigorchuk group is asymptotically equivalent to this. Bartholdi proved in 1998 that this is an upper bound, and recently Erschler and Zhang proved that it is also a lower bound. And if you look at that paper, you won't say that this is the paper in algebra at all. Random walks, all these probabilistic arguments. Now, the basic question in all these situations, groups, algebras, monoids, languages is which functions appear as growth functions of these infinite objects. I cannot help quoting, no, all finite groups grow in the same way. Every infinite group grows in its own way. That's originally Leo Tolstoy and then Gromov. So which functions? It's clear that not all functions. For example, a growth function is an increasing function. It is also submultiplicative because every word of length m plus n is a product of a word of length m times a word of length n. So the conjecture that was around for some time, well, more or less immediately after this question started to appear, was, is it enough? Is it true that every increasing submultiplicative function is asymptotically equivalent to a growth function? Bartholdi and Erschler proved that if a function lies between the growths of a Grigorchuk group and exponent, and it is sufficiently regular, which means that I don't want to list all the conditions, then it is asymptotically equivalent to a growth function of a group. Grigorchuk conjectured that there is a gap between polynomials and this function. Grigorchuk proved that this is indeed a gap for residually p groups, subdirect products of finite p groups, important class. Now let's talk about algebras and Gelfand-Kirillov dimension. Well, finite dimensional algebras have Gelfand-Kirillov dimension 0. It is clear that there is nothing between 0 and 1, because when we consider this ascending, now I'm talking about associative algebras. When we consider this ascending chain of subspaces, if they grow at every step, then we have at least a linear function. So there is nothing between finite dimensional 0 and 1. Then there is nothing between 1 and 2. It was first proved by Hedlund and Morse in 1938 in a different language. And then Bergman proved it in 1970. So now it is known as Bergman gap. Arnold had a principle that every concept is named after the second person who introduced it. I know counterexamples to this principle, when it was named after a fourth person. Bartholdi and Agata Smaktanovich proved that if gamma of n is an increasing submultiplicative function, then there exists a growth function of an algebra which is close to it. That was kind of a step. And there are much more algebras of intermediate growth than groups. No, in groups, it depends from which distance you look. But if you look from a sufficiently far, all numerous groups of intermediate growth are kind of similar to Grigorchuk group. Always some group acting on a counter set. And, but for algebras, there is a different source of algebras of intermediate growth. Marta Smith proved that if a Lie algebra L has sub-exponential growth, then its universal enveloping algebra also has sub-exponential growth. For example, if G is a finite dimensional Lie algebra, and we consider polynomials over it, So it's an infinite dimensional algebra. It's an infinite dimensional algebra of growth 1. You know, they grow linearly. So it is sub-exponential. The universal enveloping algebra also has sub-exponential growth, and it is not polynomial. From Poincaré-Birghoff-Witt theorem, it follows that only finite dimensional algebra have universal enveloping algebra of polynomial growth. Now, maybe the main result of the talk. Let f of n be an increasing function. Let us consider its discrete derivative. Theorem. It is a joint theorem with Jason Bell. Suppose that first, the derivative is greater or equal than n plus 1, which means that we don't consider linear functions. They are special and everything is clear with them. Then this derivative is submultiplicative. And third, you have this inequality, which you may ask, why doesn't it follow from being submultiplicative? Because the function f is not necessarily increasing. These three conditions. So the function is asymptotically equivalent to a growth function of a hereditary language, monoid, and an algebra, if and only if if it satisfies these three axioms, then it is asymptotically equivalent. And every growth function satisfies these three axioms. So this is a description of all functions that are asymptotically equivalent to growth function of an algebra, monoid, or language. Groups are set aside. For groups, the question is open. You see here the condition is for submultiplicativity is imposed not on the function. It is imposed on the derivative. And it is stronger. That is, if the derivative is submultiplicative, you can integrate it and get submultiplicativity for an algebra. You cannot differentiate it. Then Beery-Greenfield, after this theorem, immediately kind of did an exercise in calculus and found a function which is increasing, submultiplicative, but the derivative is not submultiplicative. So that refuted the old standing conjecture. A few remarks. The conditions that I mentioned, I listed, are not asymptotically invariant. We know the asymptotically invariant versions of these conditions, but it's technically more difficult, longer. And another remark. We have a function. We want to prove that it is asymptotically equivalent to a growth function, say of a language. So we have to construct that language. And we did it. But I must say that in these languages, there are a lot of words that are not extendable to infinite words, which is unfortunate. It would be very interesting to understand the growth of the number of infinitely extendable words. And that is very close to the so-called complexity of infinite sequences, which has been intensively studied by Google. Carlos Gustavo Moreira. It's very close. And the question is open. For example, if you count only extendable words, then the second derivative is positive. Okay. Now all subsequent unassigned results are joint results with Beery Greenfield. This paper has not yet appeared. It has been just accepted 2 weeks ago. Well, first, growth of modules. Let A be a finitely generated algebra. M is a finitely generated A module. So M is generated as a module by finite dimensional space V. Then again, we can study the growth of this module. And that is also a subject that has been intensively studied. Now the theorem, every increasing function which is less or equal than exponential is asymptotically equivalent to a growth function of a module. So there are many more growth functions of modules than of algebras. And since we understood growth functions of modules, we could answer the question formulated in the book of Krause and Lennegan. This is kind of the main question on growth, main book on growth. They asked, if you have two finitely generated modules and extension of one of them, can we say that the two finitely generated modules that are polynomially bounded to finite Gelfand-Kirillov dimension, can we say that the extension is also finite Gelfand-Kirillov dimension? Not necessarily. We have an example. Now let us talk about nil algebras. An associative algebra is said to be nil if an arbitrary element is nilpotent. In 41, Courage formulated the analog of the Burnside problem for algebras. The Burnside problem asks if you have a finitely generated group and it is a torsion group. So an arbitrary element has a finite order. Does it imply that the group has finite order? The answer is no. So Courage asked, if you have a finitely generated algebra and an arbitrary element is nilpotent, does it imply that the algebra is nilpotent and finite dimensional? The answer is also no. The first counterexample was constructed by Golod in '64, and Golod used this example to construct a counterexample to the Burnside problem. But Latyshev and Small independently asked if there are counterexamples of polynomially bounded growth, so of finite Gelfand-Kirillov dimension. If you ask if a finitely generated torsion group of polynomially bounded growth is finite, the answer is yes. It follows from Gromov's theorem. But for algebra, surprisingly, the answer is not necessarily. Tom Lennegan and Tagatos Maktonovich constructed examples of finitely generated nil algebras that were infinite dimensional and had polynomially bounded growth, but only over countable fields. Most probably they exist over uncountable fields as well, but later Lennegan, Maktonovich, and Young somewhat improved these examples and got Gelfand-Kirillov dimension to lie between 2 and 3, but it is unknown. Bell and Young proved the best of existing result for uncountable fields. For every super polynomial function, there exists a finitely generated nil algebra with this growth. Now, what are growth functions of nil algebras? Again, putting aside linear functions, which are completely clear, the conjecture is that all functions of theorem 1, so for any algebra there exists a nil algebra of the same growth, but it's only a conjecture. We can prove some approximation to this conjecture. Again, we have to distinguish between countable fields and uncountable fields. Let P of n be the growth function of the Lenagans-Maktonovich-Young algebra. So it lies in this interval. Let f of n be an arbitrary increasing submultiplicative function. Then this function is asymptotically equivalent to a growth of a nil algebra. I have to say that f of n is usually quite big, and this is an insignificant multiplier. For an arbitrary field, let delta of n be an arbitrary increasing function that tends to infinity. Let omega of n be an arbitrary increasing superpolynomial function. Then we can find a finitely generated nil algebra whose growth satisfies this inequality. Again, this is not a full proof of conjecture, but some approximation. Now let's talk about oscillating growth. Oscillating growth, something like this. Martin Kasabov and Igor Pak constructed groups with oscillating growth functions. So they oscillate between a given intermediate function, some, for example, like this, and an arbitrary rapidly increasing subexponential function. Viktor Petrogradsky from Brasilia in 21 using, well, before that he constructed analogs of Grigorchuk groups for kind of restricted Lie algebras of characteristic 2, and then in a joint paper with Ivan Shostakov we extended it to an arbitrary P. Well, anyway, he used oscillating growth, that, yes, a very good question, that it is infinitely many times less than this and infinitely many times greater than that. There are two functions that are, one of them is bigger than the other one, and the growth function is infinitely many times smaller than the small function and infinitely many times bigger than the big function. Again, there are still some open questions here. What does it mean, infinitely many? Could we say that the measure of all, say, numbers in both cases is positive? Unknown. So Petrogradsky used these examples to construct functions of oscillating growth, growth functions that oscillate between linear and those close to exponentials. But all these examples are analogs of Grigorchuk groups, and therefore they are only in prime characteristic. Together with Beery Greenfield, we constructed associative nil algebras of oscillating growth and of arbitrary characteristic, and from associative nil algebras you can get Lie algebras. So over countable fields, let f be a countable field. F is a subexponential function, so there exists a finitely generated nil f algebra such that this inequality holds infinitely many times and this inequality holds infinitely many times. Again, I could ask if both sets have positive measure. Over an arbitrary field, let f of n be Yes, yes. Let f of n be a subexponential function. Let omega of n be an increasing superpolynomial function. Then there exists a finitely generated nil f algebra such that, again, the growth function oscillates. there are even domains with oscillating growth function. So let f of n be a sub-exponential function. There exists a finitely generated domain such that this inequality holds infinitely many times for an arbitrary positive epsilon, and this inequality holds infinitely many times. Now, using these results, we could answer another question from Krause and Lennegan. If you consider tensor product of algebras, it is clear that the growth of the tensor product is less or equal than this, obvious. So, Gelfand-Kirillov dimension of the tensor product is less or equal than the sum. Warfield showed that actually the inequality may be strict. And he asked about the strongest version of this result, of his result, if the GK dimension of A is alpha and GK dimension of B is beta. Is it true that any value, then the growth function, then the GK of the tensor product always lies in this interval? But is it true that any value in this integral could be realized as the Gelfand-Kirillov dimension of a tensor product? The answer was yes, proved by Krempa and Takninsky, but their proof was a play with radicals. And so they, and independently Krause and Lennegan, asked if such examples could exist for semi-prime algebras with zero radicals. From the existence of these oscillating functions on, well, we constructed these examples. That is basically everything that I wanted to say. There is one big question, like elephant in the room. To find a new example of a group of intermediate growth. So far, there is only example of Grigorchuk group and other examples that were obtained in this way. Well, thank you.
Said the proofs are more interesting than the results. So I wonder if you could tell us about any proof of those results. Say, I wonder, there are many results in which you start with a growth function or growth class functions, and then you say, well, that's the growth function of some sort of. There are many results like this. I just would like to learn a little bit about the technique of constructing those things.
Oh, the technique.
Are they combinatorial in a sense? Or?
Well, the technique, say in Grigorchuk proof, it's an example. He describes the group and then straightforward computation. Gromov proof, it's geometric. He used Hilbert's solution of Hilbert's fifth problem. Before that, well, of course, I gave semester-long courses on Gromov proof. Now, Tits proved that there are no, he proved the question for linear groups. It follows from Tits' alternative. Now, Gromov Okay. Suppose that we have a group. We consider Kelly graph, which can be viewed as a metric space. Distance, length of every edge is 1. And the group acts on this metric space. Say, right multiplications. Then suppose that we sit on a helicopter. The helicopter goes up. All distances between elements become smaller and smaller. And when you go sufficiently far, it looks as a manifold. That is basically Gromov-Hausdorff limit. So that's how it was done. The group acts on all members of the sequence, hence it grows, it acts on the limit, which is a manifold. It satisfies the conditions of the Hilbert's fifth problem. And then you conclude that it is linear.
Suppose I give you my growth function e to the n to some power, okay, small power. Can you, from this expression, kind of concoct an algebra with this growth, or is that completely difficult to extract?
Well, in our paper with Jason Bell, more or less, it is explained how to do it. It's another question that whether it will be interesting. I mean, you construct some algebra by generators and relations, and so what? Theorem 6, okay. I will go back. Theorem 6. In the proof it is necessary. No, epsilon has to be positive. I'm not saying that it is not true for 0, but somebody else should come up with a different proof. But for our application, that was enough.
Is it a lower bound? Is it possible to go below 3/4?
Probably yes. Probably yes. We did not try very hard. We could do 3/4 itself.
These set of tools and techniques have any implication for computational complexity? Because, when you are dealing with finite generated languages, modules, fruits, and so on, automata theory, this kind of stuff, these are the tools for proving results of computational complexity. So this might be related to our
Grigorchuk group is related. It has been used a lot in questions of computational complexity. I told you that this is not just a counterexample. This is something more important. It's very difficult to say because sometimes people do the same in different languages. For example, for me, it was a pleasant discovery that Gugu and his co-authors do practically the same thing. The complexity of sequences.
I suppose it makes sense to define the Gelfand-Kirillov dimension of a group as well.
To find what?
The Gelfand-Kirillov dimension of a group.
But for groups, it is much easier because there are many more algebras of polynomially bounded growths than groups. If a group has polynomially bounded growth, it is virtually nilpotent and everything is known.
my question is whether the exponents for a group, whether it can take any real value.
Integer. Only integer.
Only integer.
But for algebras, any, say, real value from 2 to infinity.
Let's take the message.
Thank you.